Thank you very much. I know that I'm the only thing in between you and your lunch, so I'll try to be right on time, okay? So I wanna, this project is actually fully funded by the Tridurli Center, so I'm very pleased to present these results. We have not finished the test, but we're a good stage. I want to acknowledge my PhD students and the master students, Minaj, Tucker, and Shudong, and also two colleagues of mine from Europe who came actually this summer to work with us on this project. So a quick introduction, some of the results. So what we have found new, a new test method that we proposed, and then since again I'm trying to be quick, I will not repeat the conclusion, but I'll show you what we're working on right now. So as you know, there is a little bit of renewed interest in FRP bars. For bridge decks is certainly one of the major applications. I am a member of the ASTM D30 committee, and there's been right now a lot of discussion on this pull-out test method used to basically assess the bond of the FRP bars. So if you're not familiar with the method, it's a very simple method. You take a block of concrete, you embed the FRP bar with an extended part outside or at the free end, and you pull at the loaded end, and there is a bond breaker to avoid basically the cone effect. And the average tau is simply calculated as the peak force divided by the lateral bonded area of the bar. So we try to see a little bit more about this bond. And so we cast basically cylinders of concrete with the bar embedded with the same idea, but by changing the bonded length. So we use 5 diameters as the ASTM. And for the 5 diameters, we also cast the cubes just to make sure that cylinders and cubes were okay. And then we did it also 10 diameters, 20 diameters, 30 diameters, and 40 diameters bonded length. The bar was a sand-coated bar. You can see it here at the bottom with the wrap of carbon fibers. And the nominal diameters was 12 millimeters. So here you see the results. These bars basically slip inside the concrete, and the sand remains attached to the concrete and basically grooves. You can see it here and also here. It grooves the surface of the bar, leaving at the bottom of the specimen all the debris of the resin that is grooved by the sand. So we did a little bit of analysis. These are all the results for all the bonded length. In the first color here, sorry, you see also the cubes of the ASTM. So basically, you know, they work the same way. And actually, if you see here these two white lines, as you groove the bar, you basically remove the carbon wrap that is around the bar. So then we measure also the slip at the free end, and you can see that the slip starts to be noticeable at a different level of load compared to the peak if you change the bonded length. And then by coincidence, we did basically plotted something that started to scratch our heads. So what we did was we plotted the slip at the loaded end measured from the LVDTs minus the slip at the free end. So the difference between the two slips, which is basically the elongation of the bar. And to compare that, we also compare for the same load level, what would have been the elongation of the bar if you basically imagine the same bonded length pulled in tension. So of course, you should expect something like you see here, that the elongation in pure tension is more than the difference between the two slips, because in one case you're pulling and you have the same elastic strain. In the other case, the strain decreases along the bar. But for the first bonded length, the 5 diameters, the difference between the two slips was actually on the right. which was not possible, mechanically impossible. So we tried to understand why only when you increase the bonded length, you see basically this difference. So, and I want to mention here that this is the peak load versus the bonded length, that basically you see this trend, and the fourth length, the 30 diameters, was slightly off. And I should mention that because the fourth length specimen, we didn't have actually those specimens. We cut them from longer specimens. So these specimens did not have the protruding part. So the free end part that was sticking out. So we decided, is it possible that is the protruding part to have that effect? So we recast with a new bar. This one is a ribbed bar, the same specimen, all the length, the cubes. Actually, the manufacturer had two different bars with a different coating. So we casted a lot of specimens, and we tried to see if there was a difference. So what you see here is the tau, if you want, is the peak load normalized by the length, by the area of the bond, versus the bonded length. And just to compare, these are the results of the previous bar, the same coated. So we said, okay, it seems like this is the same result. But if you test the same specimen without the protruding part, without that little appendix at the end, this is what you see. So these are the green ones. So in other words, for the first length, the 5 diameters, having or not having at the end of the specimen a protruding part makes a large difference in the peak load or in the average tau, which means that this is an important factor, because when you go into the field, the manufacturers, they go to the DOT and they tell them, oh, this is my tau based on ASTM, but which one is the tau? How do I compare this material with another if the majority of the tau depends on the protruding part? And this protruding part has a different effect if the bar is different. And I want to mention here also that the current development length in ACI is probably an overestimate, and the reason being that most of the data come from the early 2000s, when the bars were completely different in geometry. So the current geometries of the bars are very different from where the data are. So then there is another problem. This is the last part that I want to mention. Again, I know that I'm the last thing between you and your food, so I'll try to be quick. So we try to consider another point. There is a lot of discussion now in ACI about the opening of the cracks with these bars. It shouldn't be as important as with the steel bars because there is no corrosion, but it's still a parameter to check when you do the design. So we came up with a new test method. Basically, it's a beam with the bar inside and a notch, and it's tested in 3-point bending. You can see here, and the bar actually extends at the two ends to measure the end slip of the displacement. We use digital image correlation. We use two different widths of the beam, but the same depth and the same length. And you can see here the results. This is the load versus the opening of the crack. And I'm going to zoom in. This is the very first part. So the responses that go down softening are the ones of plain concrete, no bar. And you can see that the bar starts to pick up the load as soon as you have the initial peak load of the plain concrete. And the difference between the two set of tests is the difference in the width of the concrete beam. So basically, the load from the bar is the picking up of the load from the bar depends on the width of the beam. These are the responses in terms of load versus vertical displacement. They're not as nice as the load versus the CMOD, the opening of the crack. And so we basically look at the same load responses using DIC. And if you use DIC, you actually have a nice response. And the reason being that, sometimes in small displacement, the sensors are not that accurate and very sensitive to any out of plane displacement. We also look at the displacement at the free end. And you can see here that basically, again, the free end moves right after the load picks up the load, and this being because of the very long effective length of this bar. But this is what I want to point out. So if you do a little bit of analysis, cross-section analysis using the data from DIC and simple equilibrium, you can get at any point of your response the load, the force in the bar. And then from DIC, if you want, you can get right at the level of the bar the opening of the crack. And the opening of the crack, except for the very small deformation, elastic deformation of the bar, divided by 2 is the slip of the bar when the crack opens. If you basically plot the load in the bar and half of this opening, which is the slip of the bar in this plot, and you plot it together with the load in the bar and the slip of the bar from a pull-out test, you see an interesting thing that for the very first part of the response here in the 35 kilonewton, which is this, which is the service load, you can actually get the a match between a pull-out test and this test with the notch beam. And what is this? Why this is important? Because there is a lot of discussion. How can I measure the relationship between the opening of the crack and the force in the bar in my beam in the field? Well, you don't need to do any tests. You can use a pull-out test, because in the service load, when the load is now more than 35 kilonewtons, the slip of the bar, and therefore times 2, the opening of the crack, can be obtained from a simple pull-out test without any fancy test. We redid this test also for the second set of bars, the one that are ribbed. And the interesting thing is, if you want here, is that you don't see, when you do this test with this new bar, the load following the plain concrete. You see that it actually goes off completely from the beginning. And the reason is because the rib bars, they have a much shorter bonded length than the sand-coated bars. So they pick up the load quite quickly compared to the sand-coated bar. With that, I want to just show you a couple of the things that, again, within this project we're doing now. And some of them actually, oh, sorry, I think it's just here we go. So some I'm going to present them tomorrow. We have done a lot of fatigue tests, and fatigue tests, I'll show that tomorrow, is actually for this bar a serious problem, even more than what is right now in the code. We're casting slabs based on the ODOT, the Ohio DOT, to actually test for fatigue. We have also done a new set of tests to go a little bit more in the details of the mechanics of this protruding part. And actually, with inverse analysis, we have obtained the shear stress slip interfacial law between the bar and concrete, which can be used for modeling. With that, I want to thank the two companies that are supporting together with Tradurli this project, and thank you for being patient and waiting for your food. Thank you so much.
Thank you, Dr. Tom.
Very nice. So I want to ask you,
so here I showed you one, but we tested 3 sizes. We tested the number 2, 4, and 7.
right? So I want to ask you, what
That's a good question. So it depends on the bar. So the sand coated was 40D, independent of the, for the first 2 sizes, the number 2 and the number 4. And for the number 7, actually was a little bit less, was 30D. For the ribbed bar, it was half of what I just told you, exactly half. So 20D for the number 2 and 4, and we're testing now the number 7. Yeah. Yeah. Yeah, it depends a lot on we saw a little bit of decrease, but it depends a lot on the bar. So you change the type of sand coating or rib, it's very different.
So, like the resin or this kind of fiber, I'm wondering whether if the literature for long-term damage, the European farmer inside the country, some kind of juice in it. So, the long run, would that?
Yeah, there has been a lot of discussion on that. What I can tell you is that in the last ACI meeting, there was a presentation about a bridge built in the early 2000s, and they did not see any deterioration, neither in the bar nor in the concrete. So in the last 20 years, basically there was almost no damage of the two materials. Yeah, yeah.